Today, our group is going to present the topic, Designing the Most Cost-Efficient Beverage Can. Our group members are PENG CHENLIN, HUANG QIZI, SHUXIN, and FANGLEI. In this presentation, each member will be responsible for one part of the project. Our topic focuses on a very common product in daily life, the beverage can. At first, a can may look like a simple container. However, in real manufacturing, the design of a can is actually closely related to cost, material usage, and production efficiency. The main purpose of this project is to find out how a beverage can be designed in a more cost-efficient way. In other words, we want to know how to use less material while still keeping the required drink volume. Our presentation follows a clear modeling flow. First, we begin with the real-world problem, which explains why beverage can optimization is important. Second, we build a mathematical model by defining the variables and formulas. Third, we use optimization methods to minimize the material required. Then we apply the model to worked example using a real can. After that, we interrupt the result and discuss its meaning in real manufacturing. Finally, we consider the limitation of the model and the possible improvement. Now let's look at the real-world background of the problem. Beverage cans can usually produced in very large quantities. Because of this, even a very small reduction in the amount of aluminum used for one can lead to a significant saving in total production cost. Most beverage cans are made of aluminum. Aluminum is a material cost for companies. If a company can reduce the surface area of each can while keeping the same volume, it can reduce the amount of aluminum needed. This is why surface area is important in our project. A smaller surface area means less material is required. However, the goal is not to reduce the drink volume. The can still needs to hold the required amount of beverage. Therefore, the real challenge is to design a can that keeps the same volume but uses the least material. A cylindrical shape is commonly used because it is easy to manufacture. So the main problem of our project is what dimensions of a cylindrical beverage can minimize the material used while maintaining a fixed volume. With this background, we can now move on to the mathematical model, while we define the variables and formulas needed to solve this problem.
Now I will explain the mathematical model for our beverage can optimization problem. Our goal is to design a can that can hold a fixed amount of drink while using as little aluminum material as possible. To make the real-world problem easier to analyze, we model the beverage can as a right circular cylinder with a circular top and bottom and one curved side surface. First, we define the variables. Let R be the radius of the circular base and let H be the height of the can. Since radius and height are physical lengths, they must both be positive. Next, we write the volume formula. For the cylinder, volume equals to the area of the circular base multiplied by the height. So the volume is pi r squared h. In this project, the volume is fixed, so the V is treated as a constant. This equation is our constraint. It means that R and H cannot be chosen independently. If the radius changes, the height must also be changed to keep the same volume. Then we build the surface area formula. Surface area represents the amount of aluminum material needed to make the can. A cylinder has two circular surfaces, the top and the bottom. Each circle has the area pi r squared, so the total area of the two circles is 2 pi r squared. The curved side surface can be unfolded into a rectangle. The width of the rectangle is the circumference of the circle 2 pi r, and the height is h, so the side area is 2 pi r h. Therefore, the total surface area of the cone is 2 pi r squared and plus 2 pi r h. So our optimization model is to minimize the surface area as subject to the fixed volume constraint V equals to pi r squared h. In other words, we want to use calculus to find the best radius and height that give the smallest surface area while still keeping the required volume. The model uses important calculus to ideas, especially functions of variables and the constraint optimization. The surface area depends on both r and h, but the fixed volume constraint connects these two variables. In the next step, we can rearrange the volume formula to express h in terms of r. So the h is equal to v divided pi r squared. After substituting this into the surface area formula, the surface area becomes a function of only one variable. Then differentiation can be used to find the critical point and determine the minimum surface area. Finally, our model has some assumptions. We assume the cone is a perfect cylinder, the material thickness is uniform, and the small practical details such as the pull tab, rim, carved edge, and the sealing parts are ignored. These assumptions make the model simpler and allow us to focus on the main relationship between radius, height, volume, and the surface area. In summary, my part builds a mathematical model. The next part will use the model to carry out the calculation and find the most cost-efficient dimensions of the cone.
Hello everyone, my name is SHUXIN and my student ID is BSC2509025. In the previous section, we established the mathematical model for our beverage can. Now, I will use calculus to solve the optimization problem and determine the most cost-efficient dimensions of the can. We begin with the volume constraint. Since the volume is fixed, we can express the height in terms of the radius, this one. Substituting this into the surface area equation gives this, and simplify into this. Now, the surface area depends on only one variable, the radius, so we can apply differentiation to find its minimum value. Taking the first derivative, we obtain this. By setting the first derivative equal to 0, we find the critical point and obtain the optimal radius. Using the volume constraint again, we substitute this result back into this. So we get height equals to radius. This means that the minimum surface area is achieved when the head of the cylinder is equal to its diameter. Now, let's look at the graph of the surface area function. When the radius is too small, the can must become much taller to maintain the same volume. As a result, the curved side surface becomes much larger, causing the total surface area to increase. On the other hand, when the radius is too large, the top and the bottom circular area increase rapidly. This also causes the total surface area to increase. Therefore, neither a very small radius nor a very large radius is optimal. There is one balance point where the surface area reaches its minimum, which is exactly the critical point we calculated. To confirm that this critical point is a minimum rather than a maximum, we apply the second derivative test. The second derivative is this. Since both the radius and the volume are always positive, the second derivative is always greater than 0. Therefore, the function is concave upward, and the critical point must be the minimum point. Finally, let's apply our model to a practical example. For a standard 330 milliliter beverage can, the optimal radius is approximately 3.74 centimeters, and the corresponding height is approximately 7.49 centimeters. Finally, we get the minimum surface area. There are the mathematical optimal dimensions obtained through calculus optimizations. In next section, my teammate will explain how these results can be applied in real manufacturing, as well as discuss the limitations and possible improvements of our model. Thank you.
I'm Li FANGLEI, student ID BSC1309022. Now, I will present my part, which is the interpretation, limitations, and improvements of our model. First, let's talk about the interpretation of our results. From the mathematical solution, we found the optimal design of the beverage can that minimizes the surface area while keeping the volume constant. This means that for a fixed amount of liquid, there is a specific relationship between the radius and heat that gives the most efficient use of material. In simple terms, this optimal design uses the least possible surface area, which directly means using less aluminum material. In real-world manufacturing, this is very important because beverage cans are produced in extremely large quantities. Even a small reduction in material per can lead to a significant reduction in total production cost. So, this mathematical result is not just a theoretical answer, but it has real industry meaning. It helps companies improve efficiency and reduce cost in large-scale production, such as beverage industries like Coca-Cola or Pepsi. Next, we move to the limitations of our models. Although our results are mathematically correct, the model is based on several ideal assumptions. First, we assume the can is a perfect cylinder, which is not completely true in real manufacturing. Second, we ignore mental thickness of the material, as well as the design of the can lid, such as the rim and pull-tab structure. Third, we assume the material cost is directly proportional to surface area, which is a simplified assumption. In reality, manufacturing also involves other constants, such as pressure resistance, durability, transportation, and bridging design. So, while our model gives an optimal theoretical solution, it cannot fully represent our real-world conditions. Finally, we discuss possible improvements. To make the model more realistic, we can extend it in several ways. For example, we can include different material codes for different parts of the can, such as the top, the bottom, and the curved surface. We can also add physical constraints, such as strength requirements or stacking stability during transportation. In addition, we can extend this into a multi-objective optimization problem. Instead of only minimizing cost, we can also consider other factors such as safety, durability, and user experience. This would make the model closer to real industry design problems. In conclusion, this part shows how calculus can be applied to real engineering problems. It helps us understand not only how to calculate the optimal solution, but also how mathematical models can be used to improve real-world decision-making. So, this concludes our team presentation. Thank you for listening.